topic is chemical kinetics. It deals with rates of reactions and their mechanisms. We'll be doing some objective questions on chemical kinetics. Let's start with question number 1. In a first order reaction, the concentration of reactant is reduced from 0.6 moles per liter to 0.2 moles per liter in 5 minutes. The rate constant is, first option 0.2191 per second, second option 25 seconds, third option 3.62 into 10 raised to minus 3, and fourth option is 0.001 per second. See, we need to apply first order rate equation here. K equals to 2.303 by T log A by A minus X. Now look at the data. The time given is 5 minutes. You need to change it to seconds. So 2.303 divided by 5 is 60 log A is initial concentration. It is given as 0.6, and B is the concentration after 5 minutes. You can take it as 0.2 here. A minus X is the left out concentration. X is the amount consumed. So A minus X is the concentration of reactant which is left out. So as per the question, what is left out is 0.2. Now if you cancel off this 2, then you get 3 over here. Log 3 is 0.477. So you get 2.303 by 5 into 60 into 0.477. This is log 3. Now this gives an answer 3.62 into 10 raised to minus 3 per second. So if you calculate this, you get this value. So the correct answer is third option. Question number 2. If the rate constant of a zero order reaction is 0.003 moles per second, the time taken for the initial concentration to fall from 0.1 to 0.075 m is. For the zero order reaction, K equals to change in concentration by T. T is the time taken. Now, what is mentioned here is rate. So what you can do is T equals to delta C by K. You can rearrange it and you get this. Now, how much is the change in concentration? It has changed from 0.1 to 0.075. So the change is 0.025. 0.1 minus 0.075 divided by K, which is 0.003. So this comes to 0.025 by 0.003. So that comes to 25 by 3, which is 8.33 per second. So the correct answer is first option, 8.33 seconds. This is the time taken for the concentration to change from 0.1 to 0.075 m. Correct answer is first option. Question number 3. In a first order reaction, 20% of reactant is consumed in 15 minutes. 20% of the reactant is consumed in 15 minutes. The rate constant of the reaction is. Let's try to solve this question. 20% of reactant is consumed in 15 minutes. Let's do it. We need to apply first order rate equation. K equals to 2.303 by T log of A by A minus X. You know very well, we have done it just now. K is the rate constant, T is the time taken, A is the initial amount, A minus X is the amount left out after time T. Now let's apply this. 2.303 by 15, the time given is 15 minutes, log of 100, you take initial amount as 100%, and 20% of reactant is consumed. So what is left out is 80%. So if you calculate this, you get the value that is 0.0148 per minute. This becomes log 10 by 8, that is log 10 minus log 8. Log 10 is 1, log 8 is 0.9. So the difference between these log 10 minus log 8 comes to 0.1. 0.1 into 2.303 by 15 comes to 0.0148. So the correct answer is third option. Question number 4. The units of rate constant of nth order reaction are, first option is moles per n minus 1, liter per n minus 1, second inverse. Second option is liter per minus n minus 1, mole per n minus 1, s per minus 1. Third option is liter per n minus 1, moles per minus n minus 1, second inverse. And fourth option is liter per minus n minus 1, moles per minus n minus 1, second inverse. The correct answer is third option, that is liter per n minus 1, mole per 1 minus n, and second inverse. That is, this is a generalized formula where n is the order of reaction. I'll write it here. Mole per 1 minus n, liter per n minus 1, second inverse. This is the generalized unit of rate constant for nth order reaction. N is order of reaction. Correct answer is therefore third option. Question number 5. For the reaction A plus B gives products, the initial concentration of A and B are mentioned below, and initial rate is also given, and from this data we need to find out the order with respect to A and order with respect to B. I'll just copy that here: initial amount of A, initial amount of B, and initial rate. With the help of this tabular form, you can arrive at order of the reaction with respect to A and B. Initial amount of A is 0.2, initial amount of B is 0.3, and the initial rate is given as 5.07 into 10 raised to minus 5. This is the first set of experiment with these initial amounts. Now, if you do the same reaction at same temperature, this time taking the initial amount of B has been changed from 0.3 to 0.1. So whatever change takes place in the rate will be attributed to B. You can see in the list it is given as 5.07 into 10 raised to minus 5. So by changing the concentration of B, you did not change A, you have changed B. By changing the concentration of B, there is no change in the initial rate of reaction. That means the rate is independent of concentration of B, or you can put it in this way: order of reaction with respect to B is 0. Order of reaction with respect to B is 0. Now let's look at the third set of experiment. Now what you have done here is you have taken 0.4, that means you have doubled this. This you have taken as 0.05, you have halved it, and it has become 1.43 into 10 raised to minus 4. Now you know very well that any change in the concentration of B is not going to affect the rate. So whatever change has taken place here can be attributed to this 0.2 becoming 0.4. So when you double the concentration, this has become 3 times. So you can say order of reaction with respect to A is 1.5. It's 1.5, and order with respect to B is 0. So the correct answer is third option. Question number 6. Consider a reaction A moles of G plus B moles of H gives products. When concentration of G and H are doubled, the rate increased by 8 times. See, when you increase both G and H, the rate has, if you double it, the rate is increasing 8 times. That means that overall order of the reaction is 3. If the concentration of G is doubled while keeping the concentration of H constant, the rate is doubled. That means order with respect to G is 1. Obviously, order with respect to H will be 2. So the correct answer is second option. Order with respect to G is 1, order with respect to H is 2. Order with respect to G is 1 because doubling G is doubling the rate, and order with respect to H should be 2 because doubling A alone is increasing the rate 4 times. So that's why it is 2. So the correct answer is second option, 1 and 2. Question number 7. The specific rate constant of a first order reaction depends on: first option, concentration of reactant; second option, concentration of product; 3, time of reaction; option 4 is temperature. Remember, rate constant, specific rate constant means rate constant K depends only on temperature. It does not depend on concentration. So, the correct answer is fourth option, depends only on temperature. K depends only on temperature. Question number 8. Which of the following statements for order of reaction is not correct? Not correct. Incorrect statement regarding order of reaction. First option, order has to be determined experimentally. This is a fact, it is correct actually. Order is not theoretical, it is determined experimentally. You need to do the reactions and find out the order of reaction. Second option, order cannot be a fractional value. Actually, this is an incorrect statement. Order can be 0, order can be even fractional. So, second option is the answer. It is an incorrect statement. Let us see third and fourth option also. Order is sum of powers of concentrations in rate law. This is correct. It is the sum of power of concentration terms in the rate equation. Fourth option, order cannot be determined from the stoichiometric coefficients of the reaction. See, by looking at the stoichiometric coefficients of any reaction, you cannot say this is the order of the reaction. So, it is impossible to make a prediction about order of reaction. You can only experimentally determine it. So, the correct answer is second option, order cannot be fractional. This is an incorrect statement. Order can be fractional value. Answer is second option. Question number 9. In a certain reaction, the rate is equal to rate constant at all concentrations of reactant. The order of reaction is, see, it is zero order reaction for which rate is always constant. So, it is always equal to rate constant. Why? Because for zero order reaction, you write rate equals to K into concentration of reactant, say A raised to the power 0. This becomes 1. So, rate is always equal to K. Rate is always equal to K. That means rate is constant throughout the course of the reaction and it is equal to a rate constant. So, the answer is first option. For zero order reaction, rate is always equal to rate constant. Rate of reaction remains constant throughout the course of reaction as it does not depend upon concentration of reactants. Question number 10. The rate constant of a reaction A gives rise to product is 2 into 10 raised to minus 2 per second. If the initial concentration of A is 1, the concentration at 100 seconds is, let us find out. This is a first order reaction. You can decide it on the basis of units of the rate constant. A gives rise to product. Now, the rate constant is, see, this is the equation, K equals to 2.303 by T log A by A minus X. Now, what is asked is the concentration at 100 seconds. So, time is given is 100 seconds, rate constant is 2 into 10 raised to minus 2. By 100 log of, what the initial concentration is 1, we need to find out A minus X. This is what we need to find out. So, this becomes, this gets cancelled, 2 by 2.303 is equal to log 1 by A minus X. So, if you take anti-log, you get the value 0.135. On calculation, you get 0.135. That is the answer for the question. That is third option, 0.135. This is the concentration left out after 100 seconds. Question number 11. During the decomposition of SO2Cl2, that is sulfuryl chloride, as per the reaction SO2Cl2 gives SO2 plus Cl2, it is observed that the initial pressure is 0.5 atmospheres and the total pressure at 100 seconds is 0.6 atmospheres. The rate constant of the reaction is, the reaction is SO2Cl2 gives rise to SO2 plus Cl2. Now, initial pressure is 0.5 atmospheres. This becomes 0. And the total pressure at 100 seconds is 0.6 atmospheres. So, what you need to do is, after 100 seconds, this is T equals to 0, T equals to 100 seconds. It is 0.5 minus P, this becomes P atmospheres, this becomes P atmospheres, because these are all gases. So, total is 0.5 minus P plus P plus P. So this gets cancelled. 0.5 plus P is equal to what is given is 0.6 atmospheres. So P equals to 0.1 atmospheres. So 0.5 minus P is equal to 0.4 atmospheres. Now taking this as initial amount and taking this 0.5 minus P as the amount left out after 100 seconds, you can find out the rate constant. So K equals to 2.303 by 100 log of 0.5 by 0.4. This gives the answer second option, 2.23 into 10 raised to minus 3. That is the value of rate constant in second inverse. You need to simplify this. Log 5 minus log 4 comes to, log 5 is 0.699, log 4 is 0.6, so that comes to 0.09, the difference, and multiply this with this, you get the answer. Answer is second option. Question number 12. The half-life of a reaction is independent of initial concentration. The order of the reaction is first option 0, second option first order, third option second order, fourth option third order. See, half-life is independent of initial concentration. It is applicable only for first order reaction. See, T half equals to 0.693 by K. This is first order rate constant. So you can see T half is independent of concentration. So the correct answer is second option, first order reaction. For first order reaction, half-life is independent of initial concentration. Question number 13. If the rate constant of a first order reaction is 1.5 into 10 raised to minus 6 per second, the half-life of the reaction is. See, this can be solved on the basis of this formula. K equals to 0.693 by T half. Here we are asked to find out half-life of the reaction. So T half equals to 0.693 by K. Now let's substitute the values. 0.693 divided by 1.5 into 10 raised to minus 6. So the correct answer therefore is first option. It comes to 4.62 into 10 raised to 5 seconds. That is the half-life of the reaction. Answer is first option. Question number 14. If the half-life of a first order reaction is 100 seconds, the time required for completion of 90% of the reaction is. See, this question can be done in two ways. You have a shortcut also. I'll first discuss with the help of first order rate equation. Also you can do K equals to 2.303 by T log A by A minus X, and we already know that K is nothing but 0.693 by T half. Now T half is given as 100 seconds. We need to find out T 90%, right? This can be taken as 100 and this can be taken as 10, because 90% completion means 10% is left out. So 0.693 by 100 equals to 2.303 by T 90% log 100 by 10. Log 100 by 10 is nothing but log 10. Log 10 is equal to 1. So this becomes 0.693 by 100 equals to 2.303 by T 90% into 1. Now T 90% equals to 2.303 by 0.693 into 100. The correct answer therefore is third option, 332 seconds. If you simplify this, you get 332 seconds. Third option. Question number 15. Sucrose decomposes in acid solution into glucose and fructose according to the first order rate law with T half 3 hours. What fraction of sample of sucrose remains after 8 hours? Half-life is 3 hours. So you can write 0.693 by T half is equal to 2.303 by T log A by A minus X. Now the T time given is 8 hours. So let's substitute the value, and we have to find out what fraction is left out after 8 hours. 0.693 by T half given is 3 equals to 2.303 by 8 log 1 by A minus X. Now you can rearrange this. 0.693 into 8 by 3 into 2.303 is equal to log 1 by A minus X. This goes 10 times, then log 1 by A minus X is equal to 0.8. So you need to take antilog of this, that comes to 0.1576. Answer is second option. Question number 16. The rate of reaction is increased by 4 times when the temperature is changed from 293 Kelvin to 313 Kelvin. The energy of activation of the reaction is, look at the way it is done. It is done on the basis of this formula, log K2 by K1 equals to EA by 2.303 R into 1 by T1 minus 1 by T2. This is obtained from Arrhenius rate equation. Log K2 by K1, it is, the rate is increasing 4 times, that means K2 is 4 times K1. So log 4 equals to EA by, we need this in kilojoules, so 2.303 to 8.314 into 10 raised to minus 3. This comes to 20 by 313 into 293. Log 4 is 0.6. Log 4 you take it as 0.6 and then simplify this, you get the value of 52.86 kilojoules per mole for activation energy. The answer is first option. Question number 17. A catalyst, option A, increases the average kinetic energy of reacting molecules. B, decreases the activation energy. C, alters the reaction mechanism. D, increases the frequency of collision of reacting species. The correct answer from these options is catalyst decreases the activation energy of the reaction and it alters the mechanism. It changes the pathway of reaction from one involving higher activation energy to the one which involves lower activation energy. So the correct answer is second option, which includes 2 statements, B and C. Catalyst decreases activation energy, changes the mechanism of the reaction. Answer is second option. Question number 18. For the reaction A plus 2B gives rise to 3C, the differential form of rate equation is. Here what you can do is, suppose you have A plus 2B gives rise to 3C. This is the reaction. As per the stoichiometry of reaction, you can say the rate of disappearance of A and the rate of disappearance of B is not same. For every 1 mole of A disappearing, 2 moles of B disappear. So rate of disappearance of B is twice the rate of disappearance of A, and rate of appearance of C is 3 times the rate of disappearance of A. So what you can write is minus dA by dt is equal to minus dB by 2 dt, and this is equal to dC by 3 dt. So you can rearrange and get different forms of these equations which are given in the options, and the correct answer is A, C and D. You get all those equations by rearranging this. This is equal to rate of reaction. So, answer is third option A, C and D. Question number 19. In Arrhenius equation K equals to A into e power minus E A by RT, the term A may be equal to K at first option very high temperature, second option zero activation energy, third option very low temperature, fourth option very high activation energy. And the correct answer is first option A and B, very high temperature and zero activation energy. When activation energy zero, it becomes zero, then e power 0 that comes to 1, so K becomes equal to A. And then at very high temperature also the activation energy can become 0 because the average energy of reactants increases. So, the correct answer is first option. Question number 20. In case of reaction ethyl acetate plus water in acidic conditions gives acetic acid plus ethyl alcohol, which of the following statements are correct? Correct statements we want to find out. Statement A, the concentration of water does not get altered as the reaction takes place. See, here we are using dilute acid. For the sake of dilute acid we need to add excess of water, so the concentration of water does not get altered. The reaction is pseudo first order reaction. Concentration of water is taken as 55 moles per liter, and D option is the liberated acetic acid is titrated against sodium hydroxide, and the correct answer is fourth option. All these statements are correct statements. Question number 21. The assertion is for the reaction NO2 plus CO gives CO2 plus NO, the rate is equal to K into NO2 square, and it does not depend on the concentration of carbon monoxide. Rate depends upon concentration of NO2, but it does not depend upon the concentration of carbon monoxide, another reactant. Reason: the rate is independent of CO because CO is involved in the fast step but not in the rate determining step. Let's write the mechanism. NO2 plus CO gives NO plus CO2. The reaction takes place like this. 2NO2 gives NO plus an active species NO3. This is a slow step. Then NO3, which is an activated species, will react with CO to give NO2 plus CO2. This takes place in the fast step. So, overall rate of this reaction is dependent on the slow step. So, rate equals to K into concentration of NO2 square. That is how it is explained. So, it's not an elementary reaction, it's a complex reaction involving two steps. The first step is slow step. So, rate equation is written on the basis of this, and the order with respect to NO2 is 2, order with respect to CO is 0 because it is involved in the fast step. Answer is first option. Question number 22. Here we have list 1 with order of reaction, and list 2 consists of various reactions, and we need to match with proper order. So, zero order reaction, let me tell you, in the list zero order reaction is decomposition of ammonia. Why? Because compounds on the surface of metal catalyst decompose by zero order kinetics, because the rate does not depend upon the number of molecules of reactants, it depends upon the number of active sites available on the surface of catalyst. So, A should be matched with 3, that is decomposition of ammonia on the surface of platinum catalyst is a zero order reaction. Now, first order, very well known first order reaction among this is decomposition of hydrogen peroxide. Decomposition of hydrogen peroxide is a first order reaction. So, C should be matched with 4, and then the reaction with 1.5 order, that is B, should be matched with reaction of chloroform with chlorine. It is 1.5 order reaction, and then third order reaction among them is NO reacting with oxygen to give NO2. So, the correct answer is the third option. Question number 23. In the list 1 we have rate and rate constant, and in the second list we have the units. For the rate of first order reaction, see, the units for rate of any reaction is same, always it is moles per liter per second. So, rate of first order reaction, the units are moles per liter per second. A should be matched with second option. Rate constant of first order reaction, the units are second inverse. So, B should be matched with first option in the list 1, and rate constant of second order reaction is rate constant of second order reaction is matched with fourth option, mole inverse liters second inverse, and for third order reaction it can be matched with mole power minus 2 liter square second inverse. We have already seen the generalized expression for the units of rate constant, mole power n minus 1 liter power 1 minus n and second inverse. So, on the basis of this you can get units of rate constants of various order reactions. So, the correct answer is first option. Question number 24. Activation energy of a reaction in kilocalories if the rate is doubled when the temperature is increased from 250 to 300 Kelvin. This question can be done on the basis of Arrhenius equation, that is log K2 by K1 is equal to EA by 2.303 R into 1 by T1 minus 1 by T2. This is how the equation, the reaction, the question can be solved. Rate is doubled, so K2 is 2 times K1, so that becomes log 2. Log 2 is 0.3, we know that. EA has to be found out. We need it in kilocalories, so R should be in kilocalories, 2 into 10 raised to minus 3, and the temperature given is 250 to 300, so this becomes 50 in divided by 250 into 300. So, on simplification you get EA equal to 2. The answer is second option. Question number 25. In reaction A moles of A plus B moles of B gives C moles of C plus D moles of D, the reactant B disappears at, first option same rate as A disappears, second option B by A times the rate at which A disappears, third option D by B times the rate at which D appears, and fourth option same rate as C appears. The correct answer is second option, B by A times the rate at which A disappears. See, you can write minus dA by dt A dt equals to minus dB by B dt is equal to plus dC by C dt equals to plus dd by d dt. So, on using this you can arrive at the answer, and the correct answer is B by A times dA by dt is the rate at which A disappears and minus dB by dt is the rate at which B disappears. So, using this you can get B by A times the rate at which A disappears. You can just interchange, rearrange this, B comes over here. So, dB by dt is equal to B by A dA by dt. Answer is second option. Question number 26. The rate constant for the first order decomposition of H2O2 is given by the following equation. Log K equals to 14.34 minus 1.25 into 10 raised to 4 divided by T. The activation energy for the reaction is. Actually, this is equation obtained from Arrhenius equation. See, K equals to A into e power minus EA by RT. So, if you apply log, then it becomes log K equals to log A minus EA by 2.303 RT. So, if you see the given equation, log K equals to 14.34 minus 1.25 into 10 raised to 4 by T. So, on the basis of this you can say that EA by 2.303 R equals to 1.25 into 10 raised to 4. So, from this you get the value of EA. Putting the value of R, you get R has to be taken in kilojoules per mole, that is 8.314 into 10 raised to minus 3. Then putting the value of R, you get the answer 239.3 kilojoules. That is the answer. So, the answer is fourth option. You get it by putting the value of R. R you take it as 8.314 into 10 raised to minus 3 kilojoules per Kelvin per mole. So, that is the answer 239.3 kilojoules per mole.